All right, this is the parametric review for the AP test. So position vector is given as either the open parentheses or angled parentheses. The velocity vector, you take the derivative in the x direction and the y direction. Acceleration is the second derivative in the x direction and the y direction. Slope of the tangent line again is dy dt over dx dt. Position, so position for y of t would be wherever it is at some given point, and then get integrating from those points. And same thing with x, you need to know your initial position and then your change in position. Speed is the magnitude of velocity, so your velocity with no direction, so you do the Pythagorean theorem. Total distance traveled is the integral of speed. And the hardest one is the second derivative. The second derivative is different. It is the derivative of the first derivative divided by dx dt. The reason why is when you take the derivative, you're doing dy dt over dx dt. So this right here, dy dx, is in terms of t. So we can't take the derivative with respect to x because the variable is t. So we have to take the derivative with respect to t, then divide by dx dt. And if you see right here, that's the same thing as d dt multiplied by dt dx, and you can see that is d dx, the derivative with respect to x. All right, so we have a position function. We want to find the acceleration. So if we're finding the acceleration, that means we're going to need two derivatives. So the first derivative is going to be the velocity. I'm going to think of this as 2t minus 1 to the negative 1. So my first derivative would be negative 1, 2t minus 1 to the negative 2 chain rule multiplied by 2. That's the velocity vector. To find the acceleration vector, that's going to be 2. And again, I'm going to have to do the power rule, then the chain rule. And this time we're going to multiply by the 2 and by the 2 again. So looking at this, the acceleration at time equals 2. It's going to be 2 in the x direction, so I know all of those are wrong. And in the y direction, I'm going to have 2 times 2 times 2, so 8 on the top. I'm going to plug 2 into the bottom, so that's going to be 2 times 2, which is 4, minus 1, which is 3. So 3 cubed, which would be 8 over 27, so A. Find the slope of the tangent line. So they already gave us dx dt and dy dt. So if I want to find dy dx, that's the same thing as dy dt over dx dt. And we're going to evaluate all of those at 2. So dy dx at time equals 2 is equal to cosine squared of 2/5 divided by the square root of 2 multiplied by the reciprocal of sine of 2 e to the 0.4 times 2, and that value works out to be 0.24509. All right, so it wants to know when the bug will be at rest. So they gave us a couple different information. They gave us the value of x and y prime. If we want the bug to be at rest, both its x velocity and y velocity need to be equal to 0. So y prime we already have. So where is y prime equal to 0? We can factor this. So the two places y prime is equal to 0 is at time equals 2 and time equals 4. We need it to also be at rest at time equals 2 for x prime. So x prime would be chain rule, pi over 4, cosine of pi t over 4, and we want to know when this one's equal to 0. Now I only really need to check 2 and 4 because those are the ones that are also where y prime is equal to 0. So x prime at time equals 2 equals pi force cosine of pi halves. Cosine of pi halves is 0, so that is in fact 0. So I know at time equals 2 it is at rest because in both the x direction and the y direction it is at rest. So let's try x prime at 4. So that would be pi over 4 cosine of pi. Cosine of pi is -1, so this is not equal to 0, so we know that 4 is not an option. So the only place the bug is at rest is at time equals 2. A particle moves along the xy plane with this position in the figure above, and we know that at time equals 7, we have this tangent line. So we know at time equals 7, we know our y position is 3. We know the slope at 7 is equal to -1. I want you to find the speed of the particle. Okay, so let's see. Speed is the magnitude of velocity. So we're going to need both x prime and y prime. So we're going to need x prime at 7. And we're going to need y prime at 7 and squared. Well, we have the x prime at 7. So dx dt at t equals 7 is 11 minus 14. So -3 squared, which is equal to 9. So I know 9 squared would then be 81. We know y prime at 7 is -1, so -1 squared is 1. So this is the square root of 82. All right, so looking at this graph, it wants to know what directions it's being moved, and it's got stuff about upright, up and down. So if dx dt is less than 0, we know we're moving to the left. If dy dt is bigger than 0, we're moving to the right. So let's look at dx dt right here. The slope of the tangent line is in fact going to be negative, so it's moving to the left. Dy dt is definitely positive here, so we're going to be moving to the right. So we're going up, up, not right. So we're going left and up. All right, here it wants the second derivative. So remember, the second derivative is the derivative of the first derivative. So we're going to do dy dt over dx dt. Dy dt is equal to 8t cubed. That's a derivative of this. Dx dt is the derivative of this piece. So that leaves us with our first derivative. Now the second derivative for parametric is a little bit different. It's the derivative with respect to t of the first derivative divided by dx dt again. So our first derivative is right here. So if we take the derivative of that, it's 8t over 3, and we're going to divide by dx dt again. So this leaves us with 8t over 3 multiplied by 1 over 6t. So simplifying that, it's going to leave us with 4/9. (17). It wants us to find the total distance traveled. So remember, the total distance traveled is the arc length, which is the integral of the speed So they want to integrate from 1 to 4. X prime squared. We got to find y prime. Y prime would be 2t to the 1/2. So y prime squared would be 4t dt. You'd integrate this in your calculator and get 15.340. Question 8. We have a particle moving on a graph where we're on x at t, y at t, where y is given by this equation and dx is given by that equation. At time equals 0, the particle's at 1, -2. As t increases without bound, what will the position of the particle approach? Okay, so if we're looking for as t increases without bound, we want to know where the particle is going to approach. We're going to need to see the limit as t goes to infinity of y of t and the limit as x approaches infinity of x of t. Well, looking at y is pretty easy because we just have a rational function. So for y of t, or y of 3, or y at infinity, the end behavior would be equal to the limit as t goes to infinity of this. Degrees are equal, so it's the ratio leading coefficient, so -3. So I know it's not c or d. Now we got to find what x is going to. Currently, we only have something to deal with x prime, but we also have an initial condition, so we know where it's starting. So if I want to find a relationship for x of t, that is going to be the integral of dx dt as we integrate that, we're going to get, it's by parts. So let's see, we'll have a derivative side, we'll have an integral side. On the derivative side, we'll have 4t. On the integration side, we'll have e to the -2t. You can take derivatives until it goes away, integrate exactly the same amount of times. Plus minus plus out the front. Draw your diagonals. So x of t, copy down them, so -t over 2 e to the -2t minus 1 e to the -2t plus c. So at time e is equal to 0, we know our position's equal to 3. So this would be 0 minus e to the 0 plus c. So that tells us c has got to be 2. So this is our position function. So as t gets bigger and bigger and bigger, this is going to 0, this is going to 0, so it's going to 2, so B. An object is moving along the curve, so it has this velocity vector, which would represent the acceleration vector. Well, if you have the velocity vector, you're going to take the derivative to get the acceleration vector. So here, my x prime is currently equal to cosine t squared. So x double prime, the derivative cosine is minus sine. Chain rule multiplied by 2t. And we're going to evaluate this at t equals 4. So x double prime at 4 is equal to -8 sine of 16. So I think immediately we know that the answer has to be C, but let's go ahead and double check the y values. So y prime was 3 minus e to the 2 over 3. So y double prime, chain rule, you'll have -1/3 e to the t over 3. T is equal to 4, so you can see, in fact, that does work. The motion of a particle in the xy plane at any time is greater than 0 can be described by the curve with the properties. We have a value for x and a value for dy dt. At which time is the line tangent to the path of the particle vertical? Okay, so first thing we're going to look at is the slope, so dy dx. That is the same thing as dy dt over dx dt. If you want a vertical tangent line, that means your slope is going to be undefined, so you're looking where dx dt is equal to 0. So dx dt is equal to 12t squared minus 48. So where is that equal to 0? So it tells us that t squared has got to be equal to 4. So t has to be plus or minus 2. We're only saying that time has to be bigger than 0, so time is equal to 2. Now we have to also make sure that the dy dt is not equal to 0 at time equals 2, because that would be 0 over 0, which is undefined. But you see here, if I do dy dt at time equals 2, we get something that's not 0. So we're not worried about our 0 over 0 case, and the only place that we have a vertical tangent line is at t equals 2. 11. The position particle that moves in the xy plane is given by the parametric equation x of t and y of t, where you've given the value for y of t, and we're giving something, I want to find x prime of t. The path of the particle in xy is shown above. What is the value of x prime of 7? Okay, so right here is our slope at 7. Our slope at 7 is -2. Oh, I'm sorry, at x equals 7. Yeah, at is -2. So remember what the slope is equal to. It's equal to dy dx is the same thing as dy dt over dx dt. So we know this slope is equal to -2. dy dt, we can find what that is. So y prime is equal to chain rule 4 minus 2t, copy down the e, and we're doing y prime at, let's see, t equals 7. So that's going to be -10 e to the 28 minus 49. And then let's see, that's going to be equal to this, -10 e to the 28 minus 49 over y prime, x prime. So you got to find out what that is, and I don't have a calculator in front of me, but it is going to be, let's see, 28 minus 49 is 21. So we're going to have 1 is equal to e to the 21 over x prime. So x prime is equal to, hold on, 5. Sorry, 5. There's a 5 here. X prime is equal to 5 over e to the 21. Okay, so this is like your free responses. It says we have a particle, it's got its position function, position at time 0 is equal to this, and we have dx dt and dy dt. Remember, when you're on a parametric in the AP test, y1, you want to put x prime. y2, you want to put y prime, which we already have. y3, you're actually going to write y2 over y1. You're going to do, I think it's alpha trace to get those. And then y4, remember this right here is your slope. And then y4, you're going to put your speed, which is going to be y1 squared plus y2 squared. So part A, write the equation of the tangent line at time equals 0. So if we want the tangent line, the first thing we need is the slope. So make sure you write dy dx is the same thing as dy dt over dx dt. Or physically write dy dt over dx dt with the equations. Either one's fine. But now you're going to have to find dy dx at a certain time. Time equals 0. So at time equals 0, dy dt is going to be, let's see, at time equals 0, y is 4. So 2 times 4, 1 minus 4/12. And same thing over dx dt. That's going to be sine of 1 over e to the 0, which is 1. So when you simplify this, it works out to be 6.3381. So that is the slope. So we have a point and a slope. So you can go ahead and find the equation of the line. So y equals 4 plus the slope, x minus the x point. B, describe the particle motion at time equals 0. So there's lots of different particle motions we can talk about. We can talk about dx dt. So dx dt at time equals 0 is sine of 1 over e to the 0, which is 1, which is bigger than 0. So since the change in x is bigger than 0, it's going to the right. We can also talk about dy dt. Make sure you tell them exactly what value. So at time equals, at y equals 0, at time equals 0, the y value is, let's see, 4. So 8, 1 minus 3/4. So that is still bigger than 0, so we know this one's going up. And then lastly, we could also talk about dRdt, but I don't think they were asking that. They were just talking about particle motions. So this goes to the right and up. Find the x-coordinate at time equals 3. So when they ask you to do this, this is really the fundamental theorem of calculus. So we know where the particle is at time 0, and we want to find where it is at time equals 3. So what you're really thinking of doing is integrating from 0 to 3. Fundamental theorem of calculus, this would be x of 3 minus x sub 0. So in general, how I think about it, if I want to find something, I have to know where I am, and then I'm going to change from those values of t. So it works out to be that the x-coordinate is going to be 3.8208. Now, I know this sounds crazy, but make sure you write everything. Right here is often worth 1 point. They will look for the limits on integration and the fact that you use the initial condition. And the second point will usually come from the value. Part D, find the limit as t goes to infinity of that. So let's look at what y of t was. So dy of t was equal to 2y 1 minus y over 12. And we want to find the limit as t goes to infinity of y of t. But looking at this right here, I'm sorry, this is d by dt, is a logistic curve. Remember, logistic looks like a product of y's if it's dy dt. So right here is your carrying capacity, and that's what it heads to. All right, so another FRQ, they've given us some values. And let's see what it says. The position of the particle in the xy is given by the parametric equations. We got that x at t is equal to y prime a square root of t, and it's known that at t equals 0, x is equal to 3. The function y of t is not explicitly known, but selected values of y double prime are shown on the table. Let R be the right Riemann sums. Using 3 sum intervals indicate in the table, show that SR is equal to that, and use SR to approximate y of 4. Okay, so if we're going to use right Riemann sums, our distance between here are 1.5. Our height is -1. Next thing, our distance between these guys is 0.5. And our value is 6. And the distance between those are 2. And our value is 5. So our Riemann sum works out to be 23/2, exactly what they said. We want to use this to find y prime of 4. So let's think, y prime of 4 would equal to y prime of 0 plus the integral from 0 to 4 of y double prime. Kind of the same formula we used for position. You're going to do the initial position and the change in position. Here, you're looking for a certain acceleration, so you use the original acceleration and the change in the acceleration. So putting that in your calculator, let's see, y prime of 0, they told you was, let's see, x of 0 would equal y prime of 0. Okay, so like I said, x of 0 will be y prime of 0. And then going over here, x of 0 we know is 3. So we know y prime of 0 is actually 3. So this is going to be 3 plus 23/2. So we know y prime of 4 is going to be 29/2. B. For t greater than 8, the nth derivative of x at t is given by that. Using the approximation for y prime of 4, find the third degree Taylor polynomial for x about t equals 16. Okay, so if we want a third degree Taylor polynomial, we're given the derivatives. So let's see, and this is centered at 16. So our P3 Taylor polynomial is going to be x of 16. Oops, that does not look like a 16. plus x prime at 16, x minus 16, I guess it'd be t minus 16 because we already have our x variable, plus x double prime at 16, t minus 16 squared over 2 factorial, and then x triple prime at 16, t minus 16 quantity squared, all over 3 factorial. So x of 16 is, so let's see, x of 16 is, so x of 16 would be y prime of the square root of 16, which would be y prime at 4, and y prime at 4 we already found out to be 29 halves. So that's what goes right here, so 29 halves. The next one is, all right, so we need to find the first derivative of 16. They gave us a derivative formula. So if n is equal to 1, that would be your first derivative. So x prime of 16 would then be 2 over 1 factorial x to the 0. I'm sorry, this was x of 16, so that is what we had here, which was 29 halves. So this will be 2 over 1 factorial times 29 halves. So that's going to leave us with 29. And now we do our second derivative. Second derivative is going to be very similar. So we're going to want the second derivative, so n is equal to 2. So x double prime is going to be 2 squared over 2 factorial, and then you're going to do x prime of 16. X prime of 16 is 29, so you're going to have 2 times 29, because 4 squared divided by 2, so it's going to be 58. And this is still over 2 factorial from this one right here. And we do the same thing for the third derivative. So the third derivative is going to be 2 cubed, 3 factorial. The second derivative at 16, the second derivative at 16 is 58 halves. So you're going to have 8 times 6, or divided by 6, and 58 halves. And then still you're going to have that 1 over 3 factorial out in front. So this is going to work out to be plus the third derivative, which is 232 over 3 t minus 16 cubed over 3 factorial. The slope of the line tangent to the path of the particle is -7 when t is equal to 16. Use a Taylor polynomial for x of t about t equals 16 to find an approximate for y prime at 16. Let's see the slope, so m, which would be equal to dy dt over dx dt. And we know the slope at t equals -7 is equal to 16. So we know an approximate for x prime of 16. We actually know exactly what it is. X prime of 16 is, now we don't have a relationship for x prime or y prime, so I'm not sure if that's the way to go. So they're telling us to use a Taylor polynomial in the previous part, part B. So we do know that y prime of 4 is equal to the same thing as x of 16. So we can plug in something 16 into here and it'll give you an approximate, which would be 29 halves.